Y- Yeah.
Okay, if everyone, welcome. If you can remember, please mute your audio. That'd be great. Um, First things first, my internet has been really, really crappy today. It's gone out probably half a dozen times. So far, we've been lucky. But if it goes out, it goes out. I'm connected by my phone, so the lecture should continue fine. You should also have the notes. I posted them up on Moodle yesterday evening, and also the audio visual assets page has every piece of video that I'm going to show. Also, by the way, if you check Moodle, there are links there to the first and the second lecture. Actually, I'm labeling this lecture 2, though it's the third lecture. The first lecture is lecture 0 because that really is kind of a fun lecture. So I don't usually number it as one of the main lectures. But yeah, those are up. You might want to check them out to make sure. I got, as I expected, copyright strikes on the second one, and I expect I'll get copyright strikes on this one as well. But since I have them, they're not monetized, and they're only available through the link. I don't think that YouTube is going to take them down. I think it'll be okay with them. We'll have to see. If they do take them down, I can always edit out the videos or just upload an audio-only recording. So there are options that we can do if they get mad at us. Okay. Any other real quick questions before we get started? Other people are saying that YouTube is having a bad day. Not YouTube, suddenly it's having a bad day. I agree with that. Okay, so the first question that we want to tackle today is whether or not intelligent machines can be constructed. We blue skied some about AGIs, artificial general intelligences, and we've said some things about them, but up till now we haven't really addressed the question of, well, can you actually build an artificial general intelligence? Is that even possible to do? The true answer is no one knows whether or not we will be able to achieve the ultimate goal of AI research. No one knows. And so if someone tells you they know, they're yanking your chain because they don't. Many people now believe it will be possible, and the more progress we've made over the last 10 years, I would say that more and more people now believe that we will achieve an artificial general intelligence. And remember, an artificial general intelligence is a computing system that behaves at the level of a human, that is able to reason, but it's general. It's not like a game playing program. It's not like a stock pick program. It's general. Okay, and that's the deal. We've never created a general intelligence. Building an AGI does not talk about whether or not it's truly intelligent or just a good fake. We started that question last time. We're going to continue with it today. Now, even though we don't know whether or not we'll ever be able to build an AGI, if you step back and you think for a moment, intelligent machines are certainly possible. How can I say that intelligent machines are certainly possible? Well, I am intelligent, I am self-aware, and I am a biological machine. So, I think, therefore I am, as Descartes phrased it. So, biologically general intelligences are possible. You're an example of one. Now, of course, that assumes that you're looking at things from a scientific perspective and not looking at them from a religious perspective or something like that. But this is a science class, so We don't entertain that possibility here in this class. Though you're welcome to do so outside of class, of course. And we all have our own personal beliefs. But if you take a scientific approach, people are intelligent. People are biological machines. Therefore, intelligent machines are possible. Just because it's possible doesn't mean we'll be able to build one. Right? Well, other than the natural way of reproducing, you can. I'm not saying that children are impossible. Clearly, children are possible. How can we? So, how does AI, the study of artificial intelligence, go about trying to create programs? Well, as we've already talked about, there are two ways of doing it: good old-fashioned AI and machine learning. Good old-fashioned AI is often called symbolic AI. Symbolic AI. And the reason why it's called symbolic AI is, well, it uses symbols, right? So when you write a computer program, you're using symbols like variables and keywords like if, and all of those things are symbols. And so symbolic AI just means AI programs written in a programming language. That's all it means. So when I say good old-fashioned AI or I say symbolic AI, all I'm doing is talking about regular old programming. Now, there are some special programming languages for AI. Prolog is an example of a AI programming language, which we may talk about a little bit towards the end of the class. Lisp and all the variants of Lisp that have grown out of it are AI-oriented languages. But you don't need a special, as we'll see, you're going to write your programs in this class in languages like Java, so you don't need some sort of special programming language. Some symbolic AI programs are set up as just ifs. So they're set up as rules. So if this occurs, then conclude this. And those languages, Prolog is an example of one of them. They were called production systems. And it's a lot like if you've taken theory of computing at this point, where we have grammars, where you have something that you match on the left-hand side, and you can replace it with something on the right-hand side. It's exactly that idea. Only the system goes and looks to see the current state of the problem and finds a rule that matches on the left-hand side. If there are multiple rules that match, it generally takes the most specific one, and then it will take some symbols in the working memory and replace them with some other symbols. But again, you don't have to have any fancy language like that. You can write it in anything. And really what we're just modeling there are if statements. So that's symbolic AI. Machine learning. Now, you might think that machine learning and neural networks are synonymous concepts, because right now, when people talk about machine learning, if someone, unless it's a technical computer science lecture, if someone talks about machine learning, there's probably a 90–95% chance that they're talking about neural networks. Neural networks are a type of biologically inspired machine learning. The model in a neural network is it's modeled on brains, on biological brains. Now, there are lots and lots of differences. It's not a perfect model, but the inspiration for the model comes from the way biological brains work, okay? Notice I'm saying biological brains. I'm not saying minds, because we don't really know how a human mind works. But we can look at the biology and model on the brain. The brain has neurons. There are synaptic gaps between the neurons. There are neurotransmitter concentrations, some neurons. Well, there's just a whole bunch of stuff that we'll talk about later. But basically, neural networks are based on brains. Okay, but that's not the only kind of machine learning. There's also a type of machine learning that does the same thing. You train it like you do with machine learning, but the underlying model is based on mathematics and statistics. And so if you look up, maybe do a quick Google search or Wikipedia, look up on hidden Markov models. That's not based on biology at all. It's based on basically statistics, and there's like a chain of stages that you go through, and they're connected together in a graph based on probabilities. But anyway, it's a mathematical, probabilistic, statistical model, but it's not one that's based on brains. So when someone says machine learning, if they're a computer scientist, they may be talking about neural networks, or they may be talking about things like hidden Markov models. There are both biological and non-biologically inspired machine learning approaches. But in general, just to be clear, there are two major approaches: symbolic AI and machine learning. And machine learning breaks down into biologically inspired machine learning and mathematical and statistical inspired machine learning. So there's sort of two subtypes of machine learning. In my notes, I give an example to be absolutely positively clear. If you were to want to do character recognition, written characters, A, B, C, etc., and you wanted to show how the approach to recognizing those characters would be different between the symbolic and the machine learning approach. Well, if you're going to do a symbolic approach, you might say, okay, if I want to do a capital A, well, there are two lines and they intersect at an angle, and I might try to characterize these line segments and the range of angles that are allowed here. I mean, the angle can't be too wide, right? It could get quite narrow, but at some point it'll be too narrow. So some range of acceptable angles there. And then, of course, an A not only has that, but it has a crossbar. So you would want to have that piece identified and talk about its angle in relation. You might say, well, the two sides and the crossbar form a triangle, and recognize that triangle. So you're trying to break it down into things that you can write programming rules about. Okay, so do these line segments, are they oriented in a way that forms a capital A? And again, for decades, for multiple decades, for almost half a century, that was the approach to trying to recognize letters. And while you might be able to make that recognize a capital A, it gets really difficult. And imagine trying to, those are printed A. Imagine trying to understand or figure out human handwriting with all of its variabilities if you're trying to use rules to describe the letters. It's pretty much impossible. Okay. Well, you can get something that works 50% of the time or some percentage of the time. Maybe let's say you could get something that worked 80% of the time. But that last 20% is just impossible because there are too many variations. And so you end up with a program that kind of works but doesn't work very well and might be limited to, say, only capital letters, right? Or might be limited to only printed capital letters in a particular font, right? Rather than handwritten letters. So that's kind of the symbolic approach. If you take a machine learning approach, well, you adopt some sort of a model. Maybe it's a neural network based on a biological model, or maybe it's a mathematical statistical model, but you adopt some sort of program that implements some kind of a learning algorithm, okay? And then you just feed it lots and lots of examples of letters, right? And by doing that, you never specify any rules for how to recognize A's versus B's versus C's. But if your learning algorithm is robust enough and you have enough training data, with enough repetitions, the learning algorithm will learn on its own, with a lot of hand-holding, to recognize those letters. And so those are the two different approaches and how they work. I may have told this story already this quarter. I don't know. I tell it frequently, but my dissertation was related to artificial intelligence. It was in fact related to something called expert systems, which were really popular in the 1980s and 1990s. And expert systems are computer programs that behave at the level of a human expert, like a radiologist or an infectious disease doctor or something like that, in a very, very narrow domain. So they can behave like a person, but only in a very tiny, tiny area. And the way those things work is it's lots of these if-then rules. You know, if the patient has a fever and the patient has little red spots, then the patient probably has chickenpox or something like that. But tons and tons of those rules that you would sit down and interview an expert and talk to them about how they diagnose things. Well, what are the symptoms of this? Well, it's usually this, and this, and that's an if rule, right? And so that's the way that worked. So that's what I did my research on. But before that, when I was looking for a topic, I had taken an AI class, a machine learning class actually. This is, again, people didn't use neural nets. So it was a class in, I said machine learning, but it was really a class in computer vision. And it was trying to use symbolic AI approaches to computer vision, and it was horrible. You know, we would spend, weeks trying to recognize cubes. It was terrible, and it was obvious to me that it would never work, right? I mean, you could get it to work in really teeny tiny areas, but it was never going to be able to, like point a camera out a window and have it identify trees and grass and cats and dogs, and you just knew you'd never make it there, not in a million years. And so I can remember talking to some of my friends in graduate school and saying, well, what I envision is, I don't know how we'll do it, but somehow we'll have to have a layer of software that'll be able to recognize the real world, take in all of the messy things like images and video and sound, and somehow be able to get those into symbols, and then we'll be able to reason about those symbols using what was called AI then, what we would now call symbolic AI or good old-fashioned AI. And so that's kind of the way I envision systems working. A lot of our current systems do really work that way. They use machine learning for low-level recognition and classification problems. So if you have a self-driving car, for example, the input from the LiDAR and the cameras and the radar and stuff like that, you've got machine learning approaches that learn to take that data and say, oh, this is a car, this is a truck, this is a pedestrian, this is a bicycle, right? Because you can't write programs for those kinds of things. But then you might have a higher level part of the system that takes in that input once it's been converted into symbols and has what are called driving policies that describe how the car is supposed to react in certain situations. And so it is this kind of a hybrid approach that you get. Now, there are some people, specifically Tesla, their approach is they're trying to move to what they call something, the software 2.0. Basically, they're in this hybrid approach, but they're trying to grow the machine learning part of it to be larger and larger, and the hand-coded symbolic AI approach smaller and smaller. And they think they will eventually get a system that has learned everything, including all of the rules of how you drive in certain situations, rather than just using the machine learning to recognize the objects that the cameras see. So that's kind of the two approaches to AI and how they interact. Right now, machine learning is best for classification or recognition problems like handwriting or images or things like that, video, taking in verbal, um, a sound stream and converting it into text, and things like that, or maybe taking text and making sounds from it, where we still use symbolic AI for more of the reasoning aspects of a program. And there's a debate about, is that going to continue, or will the machine learning component grow large enough that you can just get rid of the symbolic AI approach. Okay. Now, the next thing that I want to point out is there is an assumption underlying all of AI, whether we're talking about machine learning or we're talking about symbolic AI. There is an assumption, and the assumption is called, it goes by a fancy name, the physical symbol system hypothesis. Now, it's a hypothesis. It doesn't mean it's been proven. It means it's a thought. It's an idea. It's a hypothesis. The physical symbol system hypothesis states that physical symbol systems are capable of generating intelligent behavior. Now, what the hell does that mean? Well, first thing is, Mike, what is a physical symbol system? It sounds like a mouthful. Well, a physical symbol system is just a collection of physical patterns. Those could be marks on a chalkboard. They could be little symbols written on pieces of paper. They can be bits that are either a 1 or a 0. So, but somehow there has to be a physical manifestation of a symbol. A symbol is a pattern, okay? And that's a physical symbol system. Those patterns can be marks on chalkboard. They could be a pattern of bits. And the physical symbol system hypothesis says that a physical symbol system, this collection of physical patterns, if you take those symbols and combine them with a set of rules for manipulating those symbols, then you will be able to generate intelligent behavior. So a computer is a physical symbol system, okay? A computer is a physical symbol system. But there are other physical symbol systems. Again, when I'm making marks on chalkboard or a whiteboard, those are symbols. And if I have a rule book that tells me how to change one set of symbols for another set of symbols, well, then I am manually conducting a physical symbol system. And the hypothesis is that's strong enough, that system is strong enough to produce intelligent behavior. Now, another way of looking at it is that what I'm doing is syntactic manipulation. Remember in theory and probably in some other courses that you've had, programming languages, you've talked about syntax versus semantics, where syntax is form, okay? It's the form that you write something in. It's the actual physical symbols, the string of symbols. That's syntax. Semantics is, what do those things mean, right? Well, the physical symbol system hypothesis is saying is that just by manipulating syntax, by having symbols and rules to manipulate those symbols, you can get intelligent behavior. Now, because we have computers and because we interact with Google and Siri and Alexa and whatever continuously and, whatever, that hypothesis doesn't seem really weird right now because we already get not human level intelligence, but we get, I think we would say, some level of intelligent behavior out of our program. Certainly we do. I mean, if you have a program that can translate from English to French or French to English, that is behaving in an intelligent manner in a narrow domain. So in narrow domains, we've already achieved the goal of AI in narrow domains. We've never achieved it in a general sense, by building an artificial general intelligence. But anyway, the physical symbol system hypothesis doesn't sound crazy now, but if you think about it, it is saying something really weird. And I don't know if you guys had me for 310 for theory. I'll usually, at some point, and it's not just in that class, it's in a lot of others, I'll talk about, Arthur C. Clarke. We talked about him. He was one of the guys, that did the communication satellites and wrote with Stanley Kubrick 2001: A Space Odyssey and was involved in that. But he also has some laws. They're just things that he came up with. But one of them is a sufficiently advanced technology is indistinguishable from magic. A sufficiently advanced technology is indistinguishable from magic. And that's true. And part of the thing that's so weird about humans is we adapt so readily that that something that was magic not long ago is like, well, that's boring. And what do I mean by that? Well, you've grown up in a society in which pretty much 100% of the population is expected to be literate, is expected to be able to read and write. So from the time you were teeny tiny, your parents would read you stories, and as a little kid, you would start learning to write your name. That's one of the first things you learn. And you learn that those symbols make the sound that's your name, and that these symbols in your mind, that becomes your name, M-I-K-E. Well, that's my name, all right? Mike, that's my name. And you don't think anything about it because you grow up that way. But writing is a hugely powerful and honestly unexpected technology for a biological creature to have developed, because writing does things like let dead people speak to you. Think about it for a second. If you read the works of Plato, obviously translated, you're not going to read it in the original Greek, but if you read Plato, right, you're reading the words of someone who lived, 2,500 years ago, or whenever the fuck he lived, right? He's been dead a long, long time, but he can still speak to you. You can hear in your head his thoughts, the thoughts from a person who died thousands of years ago can be transmitted into your head. And that's done simply by some symbols that have been written on papyrus or show up on a computer screen. And that is insane when you step back and you think about it, right? But it's not insane to you because you grew up with it. But when literate societies first interacted with societies that didn't have the notion of writing, that was considered huge magic. You mean your ancestors can talk to you? That's crazy, right? I can talk to you without speaking by making some marks and handing you a piece of paper. That's crazy. Well, the physical symbol system hypothesis is just as crazy, or even more so, because you're saying that marks on paper, right, symbols, together with rules for how to manipulate those symbols, can reproduce intelligent behavior, at least in narrow domains. And again, you've grown up around computers. And, if you're 20 years old, this revolution that's happening like that's been going on for most of a decade, or a little more than a decade, has been going on for half your life. And so you're like, yeah, well, okay, sure. But when you step back, it's like, whoa. So what we're saying is that manipulating symbols, just syntactical variations, can produce intelligent behavior. And that is crazy, okay? For people a century ago or even 75 years ago, that was a huge, mind-blowing idea that you could have these machines called computers that could think. They were sometimes called thinking machines, and it's like, my God, that's insane. And now we just sort of take it for granted. But that is the physical symbol system hypothesis, and of course, more and more people now believe. Clearly, it's true for limited domains. They're called computer programs, right? But will the physical symbol system be capable of generating truly intelligent behavior? Generally, most people believe, yeah, we're going to solve the problem pretty soon now, is the thought. Of course, back in the 1950s and 60s, people thought we were going to solve the problem of general intelligence any day now, too, as we'll see here in a minute. But that is the physical symbol system hypothesis. Now, we've got to be very, very careful, because we're back to this thing about behavior, right? The physical symbol system, most people believe that it is capable of creating intelligent behavior, because we've got all these examples around us of narrow AIs, okay? They're everywhere now, okay? And we are making, you can argue we're making progress towards artificial general intelligence. You know, we now have game playing systems that can not just play one game, they can learn the rules of multiple games and become good at those. And that's only been in the last 3 or 4 years that we've done that, ever since AlphaGo. Then they came up with AlphaGo Zero, and they renamed it Alpha Zero because it can learn games other than Go, including some video games, right? So, yeah, physical symbol systems can produce intelligent behavior. However, huge question: can a physical symbol system really be intelligent? Can it be conscious? Okay. Now, we talk about that. We have a phrase for that we call weak AI versus strong AI. Now, weak and strong have nothing to do with the behavior of the systems. Okay. You can have a system that behaves in an intelligent manner, as intelligent as Mike O'Neill, or hopefully someone more intelligent. Okay, and that doesn't say whether or not the system is conscious or not. And so we reserve strong AI for systems that are truly conscious, and we use the phrase weak AI for systems that, while they may behave as if they're conscious, they may appear to be conscious, might not be. So we've got this concept of weak AI and strong AI. And the question is, does a physical symbol system, can conscious behavior arrive in such a system? And if the answer is no, well, that means that no matter how good our robots become, right, no matter how, human-like our systems may become, no matter how, human conversations they can have with us, they're not really conscious. They're just a good fake, right? They're mimicking us. They're not reproducing what we do. So that's the debate, okay? And in some sense, it seems crazy to even propose that some marks on a chalkboard and a rule book of how to change symbols on that chalkboard could be conscious. Because you look at that and you say, well, where's the consciousness? Is it in the chalk? Is it in the marker fluid that's on the board? Is it in the book? Right? I mean, where is the consciousness? But again, you know, if you try to explain writing to a pre-literate culture, someone from a pre-literate culture, that's going to seem just as weird as what we're talking about here. Because again, dead people can talk to you. Live people can talk to you too, but it's even weirder when you think dead people can talk to you through writing. So I want to address this question, but instead of me talking about the question, I think what I want to do is I want to have John Searle himself talk about this question. It's called the Chinese room argument, or the Chinese room hypothesis. So let me share my screen here, and we'll listen to a little bit of John here. Okay, I want to share screen. Let me share my screen. So you should be seeing my screen, I hope, now. And let's see, 50 to 138. Oh, reset to the beginning.
So look, I don't want to have.
And that's not the right video. Oh, Michael, and you had this all set up so nice and slick, so the students wouldn't see you here struggling with all of this, and you get here and it all screws itself up.
Understand these distinctions. In our culture, there's a big deal about objectivity and subjectivity.
And that's all the wrong stuff.
It's great to be back at Google. It is a university outside of a university, and sometimes I think this is what a university ought really to look like. Anyway, it's just terrific to be here. And I'm going to talk about I'm going to talk about a whole lot of stuff, but basically I want to start with talking about the significance of the technological advances. And Americans especially, but everybody really, is inclined to just celebrate the advances. You know, if they got a self-driving car, who the hell cares about whether or not it's conscious? But I'm going to say there are a lot of things that matter for certain purposes about the understanding of the technology, and that's really what I'm going to talk about. Now,
so that's a really good point he's making. I've tried to make that point myself for us, which is that some of these things that he's talking about, they don't have absolute answers that you can be sure of, but that doesn't mean that the questions themselves aren't important. They're actually extremely important questions. So let's see, we're going to go to 855. And now he's going to introduce his Chinese room paradox. Rather than me talk about it, I thought it was best to have him talk about it.
As you were born, a new discipline was born. It was called cognitive science. And it was founded by a whole bunch of us who got sick of behaviorism and psychology. Effectively, that was the reason for it. And Sloan Foundation used to fly us around as a lecture, mostly to each other. But anyway, that's all right. We were called Sloan Rangers, and I was invited to lecture to the Artificial Intelligence Lab at Yale. And I thought, well, I don't know anything about artificial intelligence. So I went out and bought a book written by the guys at Yale. And I remember thinking, $16.95 plus tax, money wasted. Well, it turned out I was wrong. They had in their theory about how computers could understand. And the idea was that you give a computer a story, and then you ask the computer questions about the story, and the computer would give a correct answer to the questions, even though the answer was not contained in the story. A typical story. Guy goes into a restaurant and orders a hamburger. When they brought in the hamburger, it was burned to a crisp. The guy stormed out of the restaurant and didn't even pay his bill. Question: did the guy eat the hamburger? Well, all of you computers know the answer to that. No, the guy didn't eat the hamburger. And I won't tell you the story where the answer is yes, it's equally boring. Now, the point was, this proves that the computer really understands the story. So there I was on my way to New Haven in United Airlines at 30,000 feet, and I thought, well, hell, they could give me these stories in Chinese, and I could follow the computer program for answering stories, and I don't understand a word of the story. And I thought, well, that's an objection they must have thought of. And besides, that won't keep me going for a whole week in New Haven. Well, it turned out they hadn't thought of it, and everybody was convinced I was wrong. But interestingly, they all had different reasons for thinking I was wrong, and the argument has gone on longer than a week. It's going on for 35 years. I mean, how often do I have to refute these guys? But anyway, let's go through it. The way the argument goes, in its simplest version, is I am locked in a room full of Chinese, well, the box is full of Chinese symbols, and a rule book in English for manipulating the symbols, unknown to me. The boxes are called a database, and the rule book is called a program. Coming in the room, I get Chinese symbols unknown to me. Those are questions. I look up what I'm supposed to do, and after I shuffle a lot of symbols, I give back other symbols, and those are answers to the questions. Now, we will suppose, I hope you're bored with this because I am. I mean, I've told this story many times. We will suppose that they get so good at writing the program, I get so good at shuffling the symbols, that my answers are indistinguishable from a native Chinese speaker. I passed the Turing test for understanding Chinese. All the same, I don't understand a word of Chinese, and there's no way in the Chinese room that I could come to understand Chinese, because all I am is a computer system, and the rules I operate are a computer program. And this is the important point, the program is purely syntactical. It is defined entirely as a set of operations over syntactical elements. But it's slightly more technically, the notion same implemented program defines an equivalence class that is specified completely independently of any physics, and in particular, independent of the physics of its realization. The bottom line is, if I don't understand the questions and the answers on the basis of implementing the program, then neither does any other digital computer on that basis, because no computer has anything that I don't have. Computers are purely syntactical devices. Their operations are defined syntactically, and human intelligence requires more than syntax. It requires a semantics. It requires an understanding of what's going on. You can see this if you contrast my behavior in English with my behavior in Chinese. They ask me questions in English, and I give answers in English. They say, "What's the longest river in the United States?" And I say, "What?"
Well, that's the basic idea of his premise there. And again, it's reflective of what I was discussing about symbols and things like that. But it's a lot. He really hits it home when he says, you could be answering questions in Chinese, and you don't speak Chinese. You're just moving symbols around. So, okay, where's the consciousness that understands Chinese, right? So that's good, and he's an entertaining speaker too. Well, this argument has been, like he said, argued for 35 years now. I think he came up with it in 1980 or something like that. And so, again, this talk's not that old. It's a couple of years old from Google. And the funny thing is John Searle, who's a philosopher here, is in the lion's den, right? He's giving this talk to AI researchers at Google, but he loves engaging like that. Well, he's been around forever, and so is Ray Kurzweil. They're friends, and they've argued this topic for a very, very long time. And Ray Kurzweil, he's an engineer at Google, and he's in the audience, and he gets a chance to ask his question. So let's move to that.
Can you see the video for us, please?
Can I do what?
Can you do the CC button and below so we have subtitles, please? Of the video.
No, I can try. Okay. Why, you're having problems hearing the audio on the video?
Yes, sir, but I think it's just my personal speakers.
Okay. All right, I hit the CC button. Let's see if that helps. And let's see. But when I bring my notes over, you guys aren't seeing my notes on top of the video, are you? That's a question. Like, I have my notes over the video, so
We don't see the notes.
Okay, that's great. All right, now I just wanted to make sure of that. Okay, so here is going to be Ray Kurzweil asking or debating him for a few minutes about what's going on here, and it's a pretty interesting argument in a rebuttal. So I'll give this 6, 7, 8 minutes here for John and Ray to duke it out. Okay.
Thank you, John.
I'm sorry I talk so fast, but I want to leave plenty of time for questions.
We'll start with one question from Mr. Ray Kurzweil.
Well, thanks, John. I'm one of those guys. You've been debating this issue for 18 years, I think. And I would praise the Chinese room for its longevity, because it does really get at the apparent absurdity that some deterministic process like computation could possibly be responsible for something like thinking. And you point out the distinction of thinking between its effects and the subjective states, which is a synonym for consciousness. So I quoted you here in my book, Singularity is Near, at the equivalence of neurons and even brains with machines. So then I took your argument why a machine and a computer could not truly understand what it's doing, and simply substituted human brain for computers, since you said they were equivalent, and neurotransmitter concentrations and related mechanisms for formal symbols, since they basically neurotransmitter concentrations is just a mechanistic concept. And so you wrote, with those substitutions, the human brain succeeds by manipulating neurotransmitter concentrations and other related mechanisms. The neurotransmitter concentrations and related mechanisms themselves are quite meaningless. They only have the meaning we have attached to them. The human brain knows nothing of this. It just shuffles the neurotransmitter concentrations and related mechanisms. Therefore, the human brain cannot have true understanding. So
There's some interesting variations on my original.
The point I'd like to make, and that I'd be interested in you addressing, is the nature of consciousness.
Yeah.
Because, I mean, you said today, and you wrote, the essential thing is to recognize that consciousness is a biological process like that digestion, lactation, photosynthesis, or mitosis. We know that brains cause consciousness with specific biological mechanisms. But how do we know that a brain is conscious? How do you know that I'm conscious? And how do you and how do we know if a computer is conscious? We don't have a computer today that seems conscious. It's convincing in its responses, but my prediction is we will. We can argue about the time frame, and when we do, how do we know if it's conscious or if it just seems conscious? How do we measure that?
Yeah, okay. Well, there are two questions here. One is, if you do a substitution of words that I didn't use and what words I did use, can you get these observed results? And of course, you can do that. That's a well-known technique of politicians. But that wasn't the claim. What is the difference between the computer and the brain? In one sentence, the brain is a causal mechanism that produces consciousness by a certain rather complex and still imperfectly understood neurobiological processes. But those are quite specific to a certain electrochemistry. We just don't know the details, but we do know if you mess around in the synaptic cleft, you're going to get weird effects. How does cocaine work? Well, it isn't because it's got a peculiar computational capacity. It's because it messes with the capacity of the postsynaptic receptors to reabsorb quite specific neurotransmitters, norepinephrine. What are the other two? God, I'm flunking the exam here. Dopamine, or GABA is the third. Anyway, the brain, like the stomach or any other organ, is a specific causal mechanism, and it functions on specific biochemical principles. The problem with a computer is it has nothing to do with the specifics of the implementation. Any implementation will do, provided it's sufficient to carry out the steps in the program. Programs are purely formal or syntactical. The brain is not. The brain is a specific biological organ that operates on specific principles, and to create a conscious machine, we've got to know how to duplicate the causal powers of those principles. Now, the computer doesn't in that way work as a causal mechanism producing higher level features. Rather, computation names an abstract mathematical process that we have found ways to implement in specific hardwares. But the hardware is not essential to the computation. Any system that can carry out the computation will be equivalent. Now, the second question is about how do you know about consciousness? Well, think about real life. How do I know my dog Darcy is conscious and this thing here, my smartphone, is not conscious? I don't have any doubts about either one. I can tell that Darcy is conscious not on behavioristic grounds. People say, well, it's because he behaves like a human being. He doesn't. See, human beings, I know when they see me, don't rush up and lick my hands and wag their tails. They just don't. My friends don't do that, but Darcy does. I can see that Darcy is conscious because he's got a machinery that's relevantly similar to my own. Those are his eyes. These are his ears. This is his skin. He has mechanisms that mediate the input stimuli to the output behavior that are relevantly similar to human mechanisms. This is why I'm completely confident that Darcy's conscious. I don't know anything about fleas and termites. You know, your typical termite's got 100,000 neurons. Is that enough? Well, I lose 100,000 on a big weekend. So I don't know if that's enough for consciousness, but that's a factual question. I'll leave that to the experts. But as far as human beings are concerned, there isn't any question that everybody in this room is conscious. I mean, maybe that guy over there is falling asleep, but that's no question. But what the general, it's not even a theory that I hold. It's a background presupposition. The way I assume that the floor is solid, I simply take it for granted that everybody's conscious. If forced to justify it, I could. Now, there's always a problem about the details of other minds. Of course, I know you're conscious, but are you suffering the angst of post-industrial man under late capitalism? Well, I have a lot of friends who claim they do, and they think I'm Philistine because I don't. But that stuff, we'd have to have a conversation about that. But for consciousness, it's not a real problem in a real-life case.
So you said that we haven't...
Okay, so that's a pretty good. I wanted to give you guys that because I wanted to give it to you from the horse's mouth, as it were. Instead of me summarizing, I'm like, okay, let's let John throw out his own ideas there, and rather than me summarizing Ray Kurzweil's objection to John Searle's argument, why not just have Kurzweil do it for you? So the root behind all of this, the nub of it, is that, you know, Searle was saying, well, it may appear, we may build machines that appear to be conscious, but they're just symbol systems. They're not conscious. Why do I know they're not conscious, says Searle? Because they're not biological. And right now, the only true model we have of consciousness is a biological model. So he thinks that consciousness has to run on wetware, is the way you might summarize what he's saying there. Where Kurzweil says, look, if you want to look at the biology and open up the brain, all you're going to see are neurons and neuroconcentration levels, and where's the consciousness in that? So that's their argument. That is the argument about strong AI versus weak AI. And there's no test you can run, as I said last time, to determine who's right. There's no objective test to determine whether or not there's consciousness going on there. You can look at behavior, but you can't look at consciousness. You can see two people in love, but you can't see love. Love is a concept. The two people who are in love could be in comas and not moving at all, right, and be completely immobile yet still be in love. From the outside, there's no way that you can know that, right? There's a difference between behavior and the process that's causing that behavior. Again, in the Mike O'Neill summary, because sometimes people ask, well, why do we even spend time talking about this? Because it doesn't matter. You said it's an unanswerable question. Well, the reason why we talk about it is summarized in you can't be cruel to a microwave oven. So microwave ovens aren't consciousness. You can't be cruel to things that aren't conscious. But computer systems more and more display behavior that appears conscious. So what are we going to do here? So that's kind of the weak AI versus the strong AI argument. Before I move on, let me see if there were any comments that I need to address here. Sorry, I have to slowly scroll over and see what I missed. Seems like some people were having a little bit of a hard time hearing it, but again, I see someone posted the link, because the link is in the notes. All of the links for all of these things are in the notes. Consciousness is above my pay grade. That's good. But that may be true that it's above your pay grade, but you may have to vote on laws regardless of your pay grade at some point in the future, or vote for politicians who have public positions on whether computing systems that appear to be intelligent should be given certain kinds of rights and what those rights should be. So even if it's above your pay grade, you may be pressed into service to render your vote and opinion. There's some interesting debate there, but I'll leave that to you guys to duke out amongst yourself. Yeah, good comments there. If someone wants to discuss them after class, I'll be happy to do so. Moving on. One of the questions becomes, okay, all of this is interesting and fun philosophy to talk about, but we don't have an AGI yet. Maybe we never will. But is there some test that we could have to at least determine that we succeeded or made progress towards generating an AGI? And the most famous example of that is something called the Turing test. Alan Turing, who those of you who've had 310 know all about Alan Turing because we studied Turing machines. But Turing, in addition to being doing a lot of work in early design and of computers and exploring their limitations, their capacity and limitations in his work in theory of computing, was also very much interested in AI. And so he came up with he didn't call it the Turing test, we call it the Turing test, but the Turing test, the way I like to think about the Turing test is it's kind of an acceptance test. You know, when we do software engineering, we have different kinds of tests, and one kind of test is the acceptance test. Acceptance tests are tests that the developer and the person or group you're developing the software for, they agree that if you can pass this test or these tests, then I'll accept the software because it does what we agreed, what you said you were going to do. So the Turing test is kind of an acceptance test to see whether or not you've really constructed an artificial general intelligence. We'll look at a brief little video of that, and then I'll kind of summarize it if I can find where the video is for it. Okay, that's where the video is. So now I need to share screen again. And managing all these windows. I guess Terry thought something went wrong. Let's see if I can, okay, I tried to share. Oh, did I just lose video? Somebody answer for me on the phone?
You did.
Oh, okay. Again, I told you the internet here is really, really crappy. So I think it died. Yeah, it died. Okay, but you've got your notes in front of you, so I'd like for you to look at the notes and play the video that's called the Turing test. You may be able to hear the audio if I play it because I think I've got a cached copy of it.
In 1950, the British computer pioneer Alan Turing had speculated that one day machines would think. He proposed a test, the Turing test, which a machine would have to pass before it could be considered truly intelligent. Imagine you were sitting in a room communicating via a screen with an entity somewhere else. It may be a person or a computer program. By question and answer, you have to determine whether you are talking to a human or a machine. This entity doesn't need eyes or limbs. In principle, it doesn't need a body at all. All it has to do to beat the challenge is to use language intelligently.
So that's the Turing test. It's basically
The thinking machine.
shush. Sorry, I'm not shushing you. I'm shushing my computer. The Turing test was first proposed in a paper that Turing wrote or published in 1950 called Computer Machinery and Intelligence. And if we were to think about it in a sort of a modern way, okay, an updated modern way, well, it's basically you're having a conversation with someone via text messaging, okay, or maybe Slack or whatever your current favorite messaging system is, okay. So there's no video, so you can't see the person you're talking to. There's no audio, so you cannot hear the person you're talking to, but you can exchange text messages with them, right? And so you are texting back and forth with an entity, okay? And you have to decide, is that entity a human being or is it a computing system? And if you can't truly tell the difference, then we have to say that the thing on the other end, maybe it's a person, maybe it's a computing system, but that it is behaving intelligently. And that's the Turing test. So if a computer system, just using a textual conversation, typed messages, if it can fool you into thinking that it's a person, then you've got to say, well, it is behaving intelligently, certainly as intelligently as another human. And so that's the Turing test. Now there's, you know, you might say, oh, well, I can just, you know, ask it, when were you born? You know, and if it says, oh, you know, I was created in a lab. Aha, I got you. You're not a person. Well, it can lie. Okay. And so it can say, I was born in 1987 and blah, blah, blah. And you go, oh, okay. You know, so no one said that all of its answers have to be technically truthful, right? Or you might say, well, I can give it a really hard math problem, and if it gives me the right answer right away, then I know it's aha. It's got a calculator built in. Well, yeah, but it could say, I'm not really good at math if you give it a math question. Or, you know, maybe it gives you the wrong answer. Or maybe it hesitates for a while and says, you know, the answer is 43. No, 42, you know, I mean, whatever. So that's the Turing test. Again, a lot of people have argued about it back and forth, but it stood the test of time. Pretty much it's the best kind of, quote, acceptance test that we've got to see whether or not we've created a system that behaves intelligently. Now, please notice the Turing test is a test about behavior. How is the system behaving? It says absolutely nothing about weak versus strong AI. If a program passes the Turing test, that doesn't mean that it's conscious. It's behaving as if it's conscious, but that doesn't mean it truly is conscious. So the Turing test is like an acceptance test for building an AGI, an artificial general intelligence system. What you're looking at there is, does it behave intelligently, or maybe how intelligent is it behaving? Because people have done variations of the Turing test where they like limit the amount of time you can talk to the computer system, for example. Maybe you have, you know, multiple people who are talking to it, and you have them each judge, you know, how human is the computer behaving. 1 second. Okay, I should have my video back. We'll see how long it lasts. But so you know how if you've got multiple people who are interacting with this. Oh, and I lost my background. Oh well. If you've got multiple people who are interacting with this computer program, you know, you can get each of them to like rate on a scale of 0 to 10 how human this program appears to be. And if you've got enough people, you can give it a score. And there's something called the Loebner Prize that's done. The Loebner Prize is a time limited Turing test. I think you get like 5 minutes to talk to it, and basically they'll run a bunch of programs and have a bunch of human judges that go through and try to determine how human it is. And just for fun, they mix it up because the human judges, some of the people the human judges are texting with are people, and some of the entities the human judges are texting with are computer programs. And so it is kind of funny sometimes when you get particular humans that don't score very high on the human scale. So that's kind of fun. Okay. So that's the Turing test, everything you need to know about the Turing test, but we're afraid to ask. The next sort of thing that I like to go into is beginning to look at the history of AI. So we've talked about some of the philosophical concerns. We've talked about weak AI versus strong AI. We've talked about the Turing test, which is kind of, like I said, like an acceptance test for AGI, a way to see has AI really succeeded? And a lot of people say, you know, well, when we do finally pass the Turing test, people will go and go, oh, you know, that's not a real test. I'm sure that's what they'll do. But for the last, you know, since 1950, so for the last 70 years, the Turing test has been held up as kind of the holy grail, the finish line, that if we can just get to that finish line, then we will have succeeded. So, okay, so where did AI start? Is there, you know, people have been talking about artificially intelligent machines for basically forever. Since we first started building things you could call machines, we've wondered about machines that could be intelligent. There were, I want to say in the 1700s, there were these kind of mechanical dolls that could do certain things, that like play a musical instrument, or there was one that could play chess. Well, but that turned out to be a fake because there was a midget hidden in the bottom of it that was good at chess, so he controlled the movements of the thing on the top. But anyway, people have thought about constructed intelligences pretty much forever. It's something that we've been fascinated by. But where did, and as I said, in 1950, Alan Turing published basically on computing and intelligence. So, but where is there a point that we can say, well, here is pretty much where the field of artificial intelligence came about, sort of the subdiscipline of computer science called artificial intelligence. And most people link that to the summer of 1956, and they consider that the birthday of AI, because there was a conference that was held at Dartmouth University, and it's become known as the Dartmouth Conference, held in the summer of 1956. And at that conference is where the term artificial intelligence was adopted. That is where the phrase artificial intelligence comes from. And so because of that, people tend to say, well, the Dartmouth Conference in 1956, summer of 1956, is where artificial intelligence research started. Now, it's kind of interesting because I like to point out that the Dartmouth Conference is probably the best example we have of the worst time and effort estimate ever generated in all of computing history. Now, we know it is very hard to estimate how long it's going to take to do something with a computer, right? We have all written computer programs where it's taken us far longer to write the program than we thought we should. By the way, could someone in text just ping me that you're hearing this okay? Because I realize since I joined, I haven't seen any text messages, and I didn't want to make sure I'm not just talking to myself. Okay, everybody can still hear me. That's good. Because if I had been talking to myself for the last 15 minutes, well then, that would be like any other night where I'm talking to myself. That's a joke. Although I do sometimes talk to myself. I try not to answer, however. But anyway, so I joke, but I'm not joking when I say that the Dartmouth Conference is probably the worst time and effort estimate ever given in all of computing history. Now, why would I say that? I say that because the announcement for the conference, it was an invitation-only conference, but the announcement basically said that the organizers of the conference were confident that 10 carefully chosen scientists working together for, it wasn't even an entire summer, it was like 6 weeks or something like that. They felt like they could pretty much solve most of the goals associated with the field of artificial intelligence. So they thought that it would be about, about 6 or 8 weeks, and we would have all of AI taken care of. That was 56, so this is what, 64 years later or whatever, and thousands or tens of thousands of people have been working on machine learning, and we now have computers that are billions of times faster than they have, and we still haven't built an artificial general intelligence. So I would say, when you think it's going to take you 6 to 8 weeks to solve a problem, and tens of thousands of people are still working on it 64 years later, that's not a really good time and effort estimate, in my opinion. Okay. So clearly, by that estimate, you can see that in the early days, people were very confident that we would be able to solve the problems associated with computing very quickly. And so I want to show you a video clip from the early 1960s. This is actually 1960, where people are showing you the success that they're having, okay, and why they think it's not going to be long before there are programs that behave like people. Okay, and then I do not have the ability to subtitle this one, but it's it's on your list. It's called Early Successes on your list of videos. Volume's a little low.
Hello again. With me tonight is Professor Jerome B. Wiesner, Director of the Research Laboratory of Electronics at MIT. Dr. Wiesner, what really worries me today is what's going to happen to us if machines can't think. And what interests me specifically is, can they? Well, it's a very hard question to answer. If you'd asked me that question just a few years ago, I'd have said it was very far-fetched. And today I just have to admit I don't really know. I suspect if you come back in 4 or 5 years, I'll say, sure, they really do think. Well, if you're confused, Doctor, how do you think I feel? We're just really beginning to understand the capabilities of the computer. I've got some film to illustrate this point, which I think will amaze you. And it's playing checkers against the computer, is he? Sure, it plays pretty well. Now,
while most computer scientists saw it as a mere number cruncher, a small group thought that the digital computer had a much grander destiny. Being a general-purpose machine, it could be programmed to do things which in humans require intelligence, play games like checkers and chess, and solve brain teasers.
Let's see what it's spinning up.
The field became known as artificial intelligence. And no one institution would be linked with its fortunes like the Massachusetts Institute of Technology, MIT. In 1958, 2 young mathematicians, Marvin Minsky and John McCarthy, set up a department to explore this exciting new intellectual frontier. They attracted a series of brilliant students. One of the first, Jim Slagle, got the idea of programming the computer to solve problems in freshman calculus.
Our problem boils down to integrating a complex function, which is at least most easily done, complex notation.
Jim Slagle decided to write a program which would try to solve the kinds of problems that MIT students do in the first year calculus mathematics, the problems doing what we call symbolic integrals. And he wrote a program which consisted of more or less 100 kinds of rules or suggestions. The machine would try various ones, and then it would use the special set of rules. I called them rules of fear. If the thing got too complicated, it would say, that's no good, it's too complicated. But if it seemed to be getting simpler, it would follow it further. The amazing thing, this was 1960, just a couple of years after we started, and got an A on the MIT exam, and it was frightening. It was doing as well as the average student, or maybe slightly better.
These first small exercises in artificial intelligence had turned out so well that hopes for the future were very high indeed.
So that gives you some idea. Again, I hope you were able to hear it. I put the phone here. Hopefully make it a little better. But that gives you some idea. In the early days, there was huge success. I mean, pretty much every problem that computer scientists turned their attention to, they were able to solve very quickly. And people looked at this and go, well, I mean, what makes you smart? Being able to play games like checkers or chess. I mean, you know, if you're really smart, the smartest of the smart people go to MIT. And, you know, what course, you know, it can be harder than calculus. I mean, I would think many of you, maybe Dr. Walters would disagree, but I think that many of you would say that, you know, that calculus is one of the hardest things that people do. You know, so look at that. You know, you've got computer programs that are doing, you know, as good as on making an A on the freshman calculus exam at MIT. Clearly, they're brilliant, right? So yeah, I thought that was great. So people were very excited. You got to realize, okay, that was 1960. So, you know, computers had been around 10 years, you know, in you know, maybe, you know, there were some really super primitive computers in the 40s, but really people started knowing about computers, you know, in the mid-50s. So computers were brand new. You had these huge chunks of metal. They were extremely expensive. They were very impressive, and they were like these hulking brains that were, you know, about to take over the world. And everybody pretty much thought, you know, in a few years, you're going to have computers that were, you know, smarter than people. And it didn't happen, obviously. So why didn't it happen? All right. Well, if we go back, in the early days, there were some work that went on in machine learning. There was a model, a neural network model called perceptron. We'll talk about that model in detail here in another week and a half or so. So people were looking at machine learning, but the perceptron model, while it could do a few very impressive things, there were a large number of things that it just absolutely could not do. And then there was the symbolic approach, which was seemed to be having a lot more success. But what were the techniques that people were using? Well, the techniques they were using are what have become known as, over the years, weak general methods. Weak general methods. The methods that they adopted were general, which means that you could apply them to lots and lots of different problems, from gameplay to calculus and lots of things in between, but they were weak. And what do you mean by weak? By weak, I mean they only worked on small problems. So what are these weak general methods? Well, usually they involved search, a search of some kind of a graph. Maybe the graph was a tree. The graph or the tree would represent what's called a state space model. where each node in the graph of the tree would represent a state of the problem, and the other nodes in the graph of tree would be connected by arrows, by arcs, where each of those arcs would be, if it were a game, say a move that you could make, or if it was solving a calculus problem, it would be an operation that you could apply, right? So if you model the program as a graph or as a tree, then you could use depth first search or breadth first search. You could use the stuff you learned in 325. And it would work. You could solve problems, but the problems had to be tiny. Why? Well, because the state space tends to grow exponentially in the number, if it's a game, in the number of moves that you make. And so as the problems get larger, because you're using exponential algorithms to try to solve them, you quickly find, oh, I can do 1, 2, or 3 steps. I can do 4 steps, but there's no way I'll ever do the 5th step because it's costing me 10 times as much as the previous step. So that's where the successes came from. They came from these weak general methods, and nobody knew. It became apparent after a while that the whole model they were using, the idea of searching a state space, just had limitations because you couldn't scale up the solutions. They just wouldn't scale. In addition to state space models and search, another approach that was used was logic, formal logic. We're going to cover formal logic in the second half of this quarter. Really, though, solving logic problems really gets back down to search again, and you're faced with the same kind of problems of exponential complexity. So the weak general methods had a lot of success right up front, some very impressive solutions, but they couldn't scale up. Now, people began to realize or to think that, well, maybe we can improve things if somehow we could get knowledge into our programs. And so that led to heuristics. A heuristic is a general rule that usually works. It's not guaranteed to work, but it usually works. And a heuristic incorporates knowledge. And maybe it's knowledge from experience, maybe it's knowledge from textbook. Here's an example of a heuristic. Bright red shiny apples generally taste good. If you don't believe that people use that heuristic, go into the local supermarket and see what the apples look like. They all look perfect because people want a perfectly looking apple because they think that's best. If there's an apple that's got a bruise on it, nobody's going to pick that one up because it's like, well, there's a bruise on that one. It's broken, right? Now, is it guaranteed that the bright red shiny apple is going to be tasty? Absolutely not. It's not guaranteed. But humans tend to use that. If we're talking about checkers, for example, a heuristic might be in checkers that the more pieces that I've captured from my opponent, the better off my position is. So I want to have more pieces on the board than my opponent. Is that a guarantee that you're going to win just because right now you have more pieces on the board? No. Your pieces may be lined up that there's just one, super jump move that'll wipe you out. But in general, all other things being equal, it's better in general for you to have more pieces on the board than your opponent. So that's another example of a heuristic. Another heuristic that humans use all the time that's a pretty poor heuristic, but we use it is price is an indicator of quality, right? Price is not always an indicator of quality, but people tend to believe that, well, if something costs more, it must be better. And that's why people spend more, because they don't spend more because they want to spend more. They spend more because they want the best. So price is an indicator of quality. Now, you might say, well, what does the heuristic have to do with these weak general methods? Well, a heuristic can limit the amount of search that you do. So, like if you are trying to do play a board game, right, like checkers or chess or whatever, you need a way of saying, okay, if here's the current state, if I move, we'll get to this state. Well, but how good is the state? If you don't have any way of measuring the goodness of the state compared to some of the other moves you could have made, well then you don't really know anything, right? Now, if you could play a series of moves all the way to the end of the game and look all the way to the end game along every possible path, well then you would need a heuristic because you'd know, okay, these paths lead to success most of the time. This path doesn't. So you'd know which one to choose. But like I said, the weak general methods, you can only explore so far because every time you try a different move, the number of possibilities explodes. So we can't afford to play all of the millions of possible checker games to the very end and figure out what's the best move. We can only look a few moves in the future. And then what we do is when we get a few moves in the future, those boards, since we can't search any further because we can't afford to, we apply a heuristic to say, okay, how good is this board position? And all of that information feeds its way back up, and we make our choice for our next move. And that's generally how we tend to use heuristics. And we'll talk about different kinds of search. We'll talk about hill climbing. We'll talk about the horizon effect and the need for backtracking when we get into search. Basically, the idea is that heuristics do not give you perfect knowledge. So if you want to kind of have a mental image of what a heuristic is, kind of think about it as I'm in an environment that's filled with hills and valleys, and I want to get to the top of the tallest mountain. So if I can see where the mountain is, I can walk right to it, take the shortest path. It's a straight line. But let's say now that you don't see very well, and it's kind of dim, and there's a lot of fog out right now. So I can see, but I can only see a little way. That's kind of like what a heuristic does. Your heuristic's not guaranteed to have you reach your goal, but it gives you an indication of, well, I think I'm moving in the right direction right now. So that was basically the 1960s. People were all really, really excited. They thought that success was just around the corner, and computers were going to conquer the world, and all of that was going to happen really soon now. But then, like I said, when they started really seeing that they weren't having breakthroughs, everywhere they were looking, they were finding, well, the problems become exponentially hard. And so, yeah, heuristics can help some, but what are we really supposed to do? So that optimism began to turn into pessimism in the 1970s, especially in things like vision and speech and things like that we were having very, very, very little very, very little progress on. Let's see, do I have my next video? Hold on, I got another video lined up for us. For example, here's a video from 1971, so at the beginning of the 70s, right when people were beginning to get very disillusioned of a system that could recognize objects, okay? In the video on this, the audio is again very weak, but you've got the video in your list of videos. So So let's see if we can see the video about Freddie the computer. I'll hold the phone close, so hopefully that'll help a little bit on the video, on the audio.
The University of Edinburgh, another ambitious vision project, was underway. This documentary from 1971 showed just how intractable some of the problems were. Freddie is a computer, and his world consists only of this round board and the objects on it. We immediately see this as a cup, and the computer tries.
After the first phase of processing, we have something which looks like this. The computer has sorted out the four major regions. Top of the cup, body of the cup, hole in the handle, and this irregular region, which is the shadow.
After painstakingly working out where the object ends and the background begins, the computer is ready to name what it is looking at.
Well, in teletype, you can see the results coming out.
But it took 10 minutes. A 2-year-old child would recognize it immediately.
And that was the problem. That was the absolute best that computers could do in the early 1970s, and it was pretty lame. And again, governments had been spending tremendous amounts of money on AI. Because there were all these promises, it's like, well, we can't let the Russians have AI before we have AI, right? So there was huge spending. But when you get things like that, the best you can do is, there's a board and it's got 8 objects on it, and they're all lit perfectly, and they're arranged against a white background, and it still takes the computer 10 minutes to be able to recognize, a cup from an ink pen. That's pretty sad. So what happened? Well, during this time, people pretty much gave up on problems like speech recognition, text-to-speech, automated speech generation. They gave up on that. They pretty much shied away from trying to build large-scale AIs or AGIs, and they began to turn their focus towards something that became known as microworlds. A microworld is a small, limited problem domain. Okay, and so again, remember what was the problem they were having with weak general methods? Well, it didn't scale well. So then people being faced with an insurmountable exponential wall, but being clever computer scientists, they said, maybe what we need to do is focus on small problems and see what we can do in these tiny worlds. Okay, can we solve a problem like natural language understanding if we are trying to solve it only in a tiny world? And that led to experiments like the one done by Terry Winograd, which was something called Shrdlu. Shrdlu is pretty much unpronounceable because it's missing vowels, but Terry Winograd created Shrdlu. We've got a video for that, and again, the audio level is far lower than I wish it were, but you've got a link to it in your notes, so you can play it yourself if you're not getting if you're not able to hear it yourself. So this is Terry Winograd talking about his Shrdlu program.
Terry Winograd's program, Shrdlu, could use English intelligently, but there was a catch. The only subject you could discuss was a microworld of simulated blocks.
Find the block which is taller than the one you are holding and put it into the box. In this case, it needs to do a whole set of things, one of which is figure out what is meant by words like one and it. We use those in normal everyday language in a way which has to be interpreted by looking at the context in which they appear. In this case, it types back out, by it, I assume you mean a block which is taller than the one I am holding, which is only one of several possible things I could have meant. You needed to use a set of rules of thumb about how people use words like that in order to decide
Despite Winograd's achievements, people outside AI circles were not impressed. Some predicted that artificial intelligence was doomed.
Okay, so there was Shrdlu, and you look at it and you go, okay, it could do what's called pronoun disambiguation. That is words like it or he or she or stuff like that. And you'll remember from our little from our little discussion last time, we did the little example with the Google Assistant, and with Justin Trudeau and his wife, and it could handle he and she, but only in a very narrow domain and a very narrow conversation. So, like I said, inside computer science circles, Winograd's Shrdlu was considered to be a huge success because he had solved natural language understanding, but only in a tiny, tiny world. And so people started thinking about that. What could you do with this? What could you do with this? Well, one impact, and I'm sure that Winograd didn't intend for this to happen, but by the late 1980s, right, about 10 years after his work, when personal computers were first getting started, there were adventure-type games, text-based adventures, which later became known as when they became multiplayer, as MUDs, multi-user dungeons or multi-user domains, or MOOs, MUD, object-oriented. That would have been by the 90s. But anyway, the early games were text-based, and they got pretty good. You could type in a sentence like, open the rusty lock with the red key, right? And it would understand what you were talking about. So you could, have like verb, direct object with, indirect object or object of the preposition with, and you could only talk about the little world that had been built, but some of them had pretty impressive parsers. I remember I became terribly disappointed when those games began to be replaced with graphical-based games, because quite frankly, the interactive written story that you could actually talk to the system by giving it commands, you're using your imagination to imagine the castle and all of this stuff, and that was a lot more fun, to me at least, and seemed far more realistic, because the early graphics in the late 1980s were terrible, right? And so you went from this story that you're talking to a computer and you're in the story to, it's just these little sprite graphics that look terrible. So I was kind of disappointed when things went in that direction. But now that we've got RDR2, I forgive the gaming industry for those first steps. Anyway, there were two conclusions that came out of the disillusionment of the 1970s, and I say that there were two conclusions. Maybe it's better to call them widespread beliefs. Okay, and that these widespread beliefs came from the realization that weak general methods just weren't going to solve problems. So what were these two conclusions or widespread beliefs? The first one is that knowledge is the key. It started with heuristics, but people began to say the way we've got to tackle problems is we've got to come up with ways of capturing knowledge in a computer system, especially common sense knowledge. We've got to come up with a way of capturing that. And so that work led to AI researchers coming up with things called frames and scripts. A frame is a slot and filler structure for an object like a chair with standard default values, like a chair has 4 legs. Now, if this sounds slightly familiar, it should, because essentially object-oriented programming pretty much grew out of this realization in artificial intelligence that we needed to be able to model objects and have hierarchies of objects. And that is now a standard part of programming. Almost any language, any modern language is an object-oriented language. You can define objects, you can define inheritance hierarchies, etc. Right? You can have default values, you can instantiate objects, you can modify objects, right? So there are all of these things that really, to my way of thinking, have their roots in AI researchers realizing that they needed to be able to capture knowledge inside programs, and that really led to an interest in objects that a decade or two later led to pretty much all programming languages becoming object-oriented. So even when you don't reach your goal a lot of times, you can still have extremely positive effects and positive impact. So knowledge is the key. That was one thing. And the next thing was that some small domains are valuable. Winograd's domain wasn't valuable at all, right? But there are some domains that are small but are extremely valuable, like credit card fraud detection or infectious disease diagnosis, and that led in sort of the next phase in the 1980s to the era of expert systems. And I talked about expert systems. I said my dissertation had been involved in expert systems. Well, expert systems are computer programs that function at or near the level of a human expert in a narrowly defined domain. They focused on capturing what's called surface knowledge. Just if-then rules. If this happens, then do this. They weren't concerned with a deep understanding from first principles. So you might have an infectious disease diagnosis program that didn't know anything about biology. It was just using rules that doctors had given it to be able to diagnose certain conditions, right? So these were useful, but they had drawbacks. One drawback is that they were very brittle, meaning that if you gave it a situation that was not specifically what it was programmed for, you'd get crappy answers. So like you have an infectious disease diagnosis program, but you can't ask it anything about heart conditions, right? Because that has nothing to do, well, it's medicine. And a human would say it's got a lot to do with infectious disease diagnosis because they're both medicine, but the program would just have if-then rules for infectious disease diagnosis, right? So they were very brittle, and even worse than being brittle, they didn't understand. They have no way of knowing when you're asking them something that they don't know about, and so they tended to just you ask them things that were directly in what they had been programmed for. They could give you good answers, but if you asked them anything outside that, you'd get terrible answers. And they couldn't even tell you, well, this is outside my range of expertise. And even worse than that is they didn't learn. All of the knowledge was hand-coded by humans, right, who had written the program, the expert system program. So human knowledge changes over time. So expert systems, you needed people to maintain them. And as new information came along, to incorporate that. And sometimes it's real hard because new information comes along that invalidates the old way of doing things. And so expert systems had their problems, but they were sort of the first example of an AI application that was commercially successful. And like I said, credit card fraud detection, looking at behavior, spending patterns, and noticing when a charge on a card doesn't seem to match a pattern of the user of that card. So that was the era of expert systems in the 1980s. So we're gonna call it quits here because we're out of time. But next time I'll finish up the history, and we'll start looking at particular applications, machine learning applied to translation, natural language understanding, computer vision in more detail, and autonomous vehicles. So that's where we're going to pick it up here next time. I had fun. I hope you had fun. I'm going to, as I normally do, I'm going to stop the recording at this point. Lecture's over, but I will entertain questions after the fact for those of you who have questions and would like to stay for a while. So thank you for attending. I'll see you guys. This is Thursday. I'll see you guys on Tuesday. Take care. Bye-bye. Have a good weekend.